This is lesson 31 of the Quantum Mechanics, a mini lecture series, continuing on from last lesson on the Taylor series expansion of e to the x. So e to the x I showed you was something like this: 1 plus x squared over 2 factorial plus x cubed over 3 factorial dot dot dot. Okay, it can be represented as like a infinite series of terms. Now I'm going to introduce the idea of I. Okay, I is an imaginary number. Okay, I stands for imaginary unit or imaginary number. It's basically the square root of -1. Okay, so we lied to you in junior high school that you can't take the square root of negative. Well, you can. There's a whole branch of maths called complex numbers, and it allows us to work with and manipulate numbers, okay, like this, okay, which aren't defined in the real number system. The real number system, real numbers like 1, 2, 3, e, pi, dot, dot, dot. So e to the ix, okay, so if we have e to the x, e to the ix is just the same thing but with an I, okay, before the x, okay, so it's the I is the coefficient, the thing in front of the x, plus ix cubed over 3 factorial plus dot, 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 okay, noting that I squared is -1, okay, because I times I, square root of -1 times the square root of -1, you actually get a real number, -1. And I cubed is just -1. Right, so therefore the Taylor series expansion of e to the ix is just 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial dot, dot, dot. Okay, and so a complex, there are things called complex numbers. So a complex number can be represented like this: z equals I plus x y. Okay, if we were to plot it, so suppose we've got a complex number, z is equal to I plus, let's say, better if I write it like this actually, a plus ib. Okay, a is the real part. This is a complex number. Complex number because it involves a real part, a, and an imaginary part, b. An example, suppose we've got 3 plus 2i. The real part of this complex number is 3. Okay, real because we can do things with a 3. And the imaginary part is 2. Okay. If we were to plot it, y-axis, we can call it the imaginary, IM for short, imaginary axis. X-axis, we can call it the real axis, RE. If we plot that, so suppose we've got 1, 2, 3, imaginary, we go up by I, 2i, 3i, and so on and so forth, minus I, minus 2i, minus 3i, minus 1, dot, dot, dot. So 3 is here on the x-axis, 2i is up here, so put a dot, and there we have it. That's our complex number. We draw a line there with an arrow sometimes, right? There you go. So that's a complex number, just a little deviation from our discussion. Just interesting to know. Okay, if you had something like -1 minus I, okay, -1's down here, minus I's here, put a dot, and there's your complex number. So let's continue with our discussion on the Taylor series expansion of e to the ix. We can actually separate it out and put the imaginary terms together. So if you were to expand it, right, further than I did here, okay, beyond the ix cubed over 3 factorial, you get something like this: minus dot, 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 plus I, put the plus here, plus, I'm running out of room, plus I, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus dot, dot, dot. That's the real part, and that's the imaginary part. Okay, so that's what e to the ix looks like. Okay, it can be represented as a Taylor series expansion involving infinitely many terms.